Okay. Okay. So I will. Good afternoon, all. From the last few lectures, we are discussing the destructive testing methods and non-destructive testing methods. And from that destructive testing methods, in today's session, we are going to discuss the fatigue test. In this, we will try to understand how the fatigue failure of a component is occurring, or why the fatigue failure of a component will occur. And then after that, what are the different types of the stresses or stress cycles are there. Then after that, how to test the fatigue life, or you can say that fatigue limit or fatigue strength of a component. For that, we are going to conduct a fatigue testing. Then after that, we are going to see the fatigue curve for ferrous materials and for non-ferrous materials. Then whichever fracture is appearing there in this fatigue test, we are going to study the nature of that fracture appearance. Then there are certain methods to protect this uh, f- fatigue in that particular component. You can protect that, but you can avoid that by certain methods. You can use that. There are 5 to 6 different factors that you have to control to avoid this fatigue failure in the component. Means you cannot avoid it completely, but you can control it slightly. Then there are certain factors. On that factors, the fatigue life of a particular component depends. That factors we are going to discuss. Okay. Now, the first very important point in this, what is the meaning of the fatigue failure? Okay, this fatigue failure, I have written that in this slide. Okay, you can read it. What is the fatigue failure? And I have here written some examples also and some causes. These are the causes of occurrence of that fatigue failure. Now, what is the fatigue failure? Here, in short, you can say that a component uh, may get failed below its ultimate tensile strength. Okay, sudden failure of a component below its ultimate tensile stress due to fluctuation in the stress. Here, main reason for the fatigue failure is fluctuation in the stress. Okay, this is the main reason. Sometimes it may be at the higher level, sometimes the stresses may be at the lower level. That I will explain in the later. Means in the next slide, we will understand what type of the stresses will be there. Okay, different stress cycles will be there. In short, you have to understand that uh, here variation in the stress is there. Variation is nothing but they have used here word the fluctuation. Okay, continuous or frequent fluctuation in the stresses, the material will get failed below its whichever ultimate or its tensile strength value is there. Below that stress value, it will get failed. This failure is termed as the fatigue failure. Now, this fatigue failure is very common in the rotating machine parts. You can, for example, you can write rotating machine parts. Like for example, you can say that the different turbines are there, compressor, pumps, different kinds of the springs and connecting rod. In all these components, this type of fatigue failure may occur. Then what are the common causes for occurrence of this fatigue failure? These are three common causes are here. There's three common causes. You can, in short, you can write these three common causes as a stress fluctuation. Okay, these three if you combine these three common causes, it will result in the stress fluctuation. Now, first is applied stress. Whichever stress is there, it should be of the sufficient magnitude. Then large variation in that applied stress value will be there, and a number of cycles of that applied stress. Okay, now these are the three factors that will cause the fatigue failure. Okay, we will discuss these three causes in detail with the help of the type of the stresses. Depending on this type of stresses, of if you understand this type of stresses, you will understand that in this fatigue failure, three types of the stresses will be there. You can see the first diagram, that is below that. Here you can say it is termed as A. Okay, this is the A, and this stress cycle is termed as a reversed stress cycle. Okay, reversed stress cycle, or it is also known as tension compression cycle. Okay, continuous cycle will be there, having tension, then compression, then tension, then compression. This will be repeated, means tension compression cycle will be there. This is termed as reversed stress cycle. Okay, tension compression cycle or a reversed stress cycle. Then the next cycle is a repeated stress cycle. Repeated stress cycle is nothing but only tension will be there, but magnitude of that tension stress will be different, or tensile stress value will be different. Okay, here it is, you can understand from this diagram. Okay, these two diagrams you can compare it. This first diagram is a reversed stress cycle. This reversed stress cycle is also known as tension compression cycle. Okay, some tensile stress, some compression stress, then again some tensile stress, some compression stress. This part will be, means tension compression, that part will get repeated again and again. This is termed as a reversed stress or tension compression stress cycle. The next type is, here only tension will be there. Okay, this is termed as the repeated stress cycle, or it is also known as tension cycle. Only tension or tensile stress will be there. And third, it is not having a means stress value is irregular here. That's why it is termed as irregular or random stress cycle. It may be of tensile nature, or it may be of compression nature. Stress may be of tensile nature, or it may be of compression nature. Okay, that's why it is termed as irregular or random stress cycle. So these three types of these stress cycles may be there. And here you can understand that fluctuation in the stress or applied stress is varying all the way, means throughout that cycle, or throughout the life of that component, or throughout the particular time period, continuously that component is subjected to the fluctuating stress, and it may be tensile in nature, or it may be compressive in nature. Now a component may get failed due to these fluctuating stresses before its ultimate tensile stress value. Okay, if suppose a component is having some higher tensile strength value, even though it may get failed to the lower tensile strength values or lower stresses values, due to this fluctuation in the stresses, due to the fluctuation in the stresses. And why this is happening, these components are rotating components. Only you can say that in short, the rotating components, they will, in the rotating components, failure is occurring due to this fatigue only. Okay, due to the fatigue only. And this fatigue is caused due to the fluctuation in the stress values. And then the next step is how to check the fatigue strength, or you can say that the fatigue limit, or in some books they have mentioned the endurance limit also. Now here two important terms will be there. You can say that the fatigue limit and fatigue strength. Fatigue limit and fatigue strength, two important terms will be there, and these are a little bit confusing here. You have to understand that. I will repeat it again. The fatigue limit or endurance limit, uh, it is related to the ferrous alloys. And fatigue strength or endurance strength is related to the non-ferrous alloys. Okay, there may be some object, they may ask you in this some objective questions. Then why these terms are related to the ferrous alloy, why the fatigue limit or endurance limit is related only to the ferrous alloys, then why this fatigue strength or endurance strength is related to the non-ferrous alloys, that I will tell you after discussing the setup of the experiment. After that, I will tell you the reason behind that. Here only you have to remember that the fatigue limit or endurance limit, fatigue limit and endurance limit, these two are same terms. Fatigue limit is also known as endurance limit, and this is related to the ferrous alloys. And fatigue strength or endurance strength, it is related to the non-ferrous alloys. Okay, so before discussing the actual definition of that fatigue limit and fatigue strength, before that we will move towards the setup which we are going to use to test to conduct the fatigue testing. Now, whichever machine arrangement here, you can see the machine arrangement is here. Here, some loading is there. This is your component. This is the specimen. You can say that this is the specimen under the specimen on which we are going to conduct the test. This is the loading, and here you have to rotate that part. Here we are providing some machines, you can say that different motors you can use to rotate that component from one end. We are applying the loads, and from one other end we are rotating that component. Okay, and after that we are going to uh, observe when that component get fails, and at the end we are going to test its means we are going to find the stress value, and that stress value when the component fails, it will be termed as the fatigue limit for a non ferrous components, and it will be termed as fatigue strength for non ferrous components. Okay, you can draw these diagrams. I will wait for 1 minute here. Please draw the diagrams, and after that we will discuss the next part. After completing the drawing, please mention that in the chat box. Prajwal is there? Prajwal, Prajwal or
Yes, sir.
kindly can you record that video for attendance?
Yes, sir.
Okay, okay. Please record it. Okay, I think you may have completed the drawing. I will explain the, you can continue the drawing. I will just explain the setup used. Now, the now here to test the fatigue developed in the component. Here generally we are using the testing machine. That machine is termed as Wohler's testing machine. Here I have written the name also, Wohler testing machine. Or if you are not able to remember this name, you can directly write the fatigue testing machine also. But generally, commonly, this Wohler's testing machine is used to test or to check the fatigue developed in the metal component. Now, okay, and now again, here you can see the arrangement here. The specimen used here, you can see that this is the specimen used here is used in the form of a cantilever beam. Okay, cantilever beam in the sense one end is fixed and from other end loading will be done, or you can simply in one end is fixed and other end is free. Whichever specimen we are using here, we are using in the form of a cantilever beam. Here that cantilever beam you can see in this second diagram, you can see that cantilever beam, one end is fixed, here we are rotating, means this is that end where we are rotating it, or you can say that this is the fixed end, and from other end we are applying the load. Okay, from other end we are applying the load. Here also this is the specimen, one end will be here, this is the fixed end. From this side we are going to rotate it with the help of the motor, and from this side we are going to apply it, the load. Okay, the specimen, I will repeat it, specimen used for checking the fatigue developed in that particular metal, it will be used in the form of a cantilever beam. uh, the cantilever beam means the specimen will be fixed from one end, and from other end a loading or load will be applied, and whichever end is fixed, from that fixed end we are going to rotate that component, and while rotating that component we are also going to count the rotations. Okay, that will be termed as the number of rotating cycles or number of rotations. Okay, and we will go, we will continue with this, means sometimes you have to change this stress, or you will apply a particular amount of load, and for that particular amount of load you are continuously or step by step you are going to rotate the component. What will happen during this rotation? There will be some variation in the stresses. Okay, these type of stresses will get created. Okay, from this side we are applying the load here, and from the other end we are rotating the component. Then what will happen here? The upper surface of the specimen, here you can clearly see it from this diagram. The upper surface of the specimen is subjected, or it is under tension. Upper surface, this dotted line you can consider it as a its axis or neutral axis. The upper surface of the specimen, it will be under tension, and lower surface will be under compression. Okay, this dotted line is the neutral axis. Above that, the surface will be under tension, and below this neutral axis the surface will be under the compression. Then there will be a stage. After continuous, step by step, we are going to rotate the component. Step by step we are going to rotate this. This will be termed as the number of rotations, we are going to say that. And it will be termed, or it will be denoted by letter n. Okay, it will be denoted by letter n, and that stress value will be denoted by s. Okay, please listen me carefully. Whichever stress you have applied here, it will be denoted by s. And number of rotations here, whichever rotations you are applying, that will be denoted by letter n. Number of cyclic fluctuations, you can say that number of cyclic fluctuations in the stress. Due to that rotation, there will be stress fluctuation due to rotation of the component from one end. Okay, we are continuously providing one by one rotations you are doing here. Due to this rotation, fluctuation in the stress values will get created. That's why it is denoted by the letter n. And this n is nothing but number of cyclic fluctuations occurring in the stress. Okay, whichever rotations are there, that's simply denoted by letter r, rotations. And whichever fluctuation in the stress will be there, that will be denoted by the letter n. And letter s will indicate the stress value. Okay, and at the end you will when that at a particular stage will come, when that component will get failed. Okay, at a particular point that component will get failed. At that time, your fatigue test will get completed, and at the end of this you will get a curve, that is the SN curve. Okay, you have to plot the stress against the number of cyclic fluctuations. Okay, number of cyclic fluctuations and stress is plotted, and you will end up with a curve. Okay, this type of curve you will get. That curve will be termed as the fatigue curve, or in some books it is also mentioned as SN curve. Okay, this is the stress, and this is the number of cyclic fluctuations. Okay, number of cyclic fluctuations, that will be termed as the SN curve, or it is also known as the fatigue curve. And here two types of the fatigue curves are shown in this diagram. The top curve is for the ferrous metals and their alloys, and the bottom curve is for non-ferrous metals and their alloys. Now we will discuss what is the reason behind this nature, why that you can say that the stress value is higher for ferrous metals and why it is lower for the non-ferrous metal. I will discuss it. You can draw this curve also. Please draw this curve. While drawing this curve, you can listen few more important points here. okay, related to the number of cycles. Okay, number of cycles of that rotations are required. Okay, number of cycles whenever you have used the higher stress. Okay, from one end we are applying the higher stress. Okay, just for few seconds here, from one end we are applying the load or stress. Okay, whenever this load or the stress values are higher, then number of you can say that the cycles, number of cycles to cause failure, it will be lesser. Whenever load is higher or stress is higher from one end, the number of cycles required for the failure will be lesser. And whenever the stress, or in other word, whenever loading is less or stress is less, the number of cycles required for the failure of that component will be more. Okay, this is very important point related to the stress and the number of cycles required for the failure. Whenever stress is more, number of cycles required for failure will be less. And whenever stress is less, the number of cycles required for failure will be more. Okay. Okay, now the two important terms which I have already earlierly mentioned, what is the fatigue limit or endurance limit, and fatigue strength or endurance strength. Okay, that we will discuss here. Now, during the performance of this fatigue testing, the stress value, okay, there is a particular stress value where there is a particular stress value. Okay, I am explaining this for ferrous materials. Okay, ferrous metals and their alloys, there is a particular stress value where fracture does not occurs. Okay, fracture does not occurs for infinite number of the cycles. Okay, if you do the infinite number of the rotations also, there is a particular stress value. And suppose you have applied one stress, suppose x value of stress, and from other end now you are rotating that component. Okay, now if you perform that rotation infinite number of times, also it does not result in the failure of that component. That particular value of the stress is termed as the fatigue limit or endurance limit. Okay, a particular value of the stress will be there, and if you apply infinite number of the rotating cycles, then also it does not result in the failure of that component. That particular value will be termed as the fatigue limit or endurance limit, and this occurs only in case of the ferrous materials and their alloys. You can say different types of the steels, iron, steels, and ferrous alloys. Okay, this is the fatigue limit or endurance limit. For a particular value of the stress, if you apply infinite number of the rotations, then also there will not be any failure of that component. That's why that particular stress value is termed as the fatigue limit or endurance limit of the component. Okay, and this occurs only in case of the ferrous materials and their alloys. Okay, if you apply infinite number of the rotations, then also there will not be any failure of that disturbance. uh, okay, for when you conduct the similar test, suppose for a particular stress is there, and if you are providing the number of rotations, Then in case of the non-ferrous alloy, after certain number of rotation, that component may get failed. Component may get failed. Okay. Here, in case of the ferrous materials, if you provide infinite number of rotating cycles, then also failure of component does not occur. That's why that particular stress value is termed as fatigue limit or endurance limit. But in case of the non-ferrous alloys, suppose magnesium alloys, copper alloys are there, lead alloys, tin alloys are there. In that case, what will happen here? Just only if you decrease the load, just you have to increase the number of rotating cycles. At a particular point, that component may get failed. Okay, uh, that's why whichever higher amount of load is there that a particular non-ferrous material can carry without the failure, that value will be termed as the fatigue strength or endurance strength of that component. It may get failed after certain number of rotations, okay, for that particular stress value. And whichever higher amount of stress value is there without failure, that value will be termed as the fatigue strength or endurance strength for non-ferrous materials and their alloys. But in case of the ferrous materials and their alloys, for a particular value of stress, if you provide infinite number of rotations also, then that component is not going to show any kind of failure. Okay, that's why that corresponding value will be termed as fatigue limit or endurance limit, and that is the case for only ferrous materials and their alloys. Okay, so this is the fatigue limit or endurance limit for ferrous materials and their alloys, and fatigue strength or endurance strength for non-ferrous materials and their alloys. For example, you can say that magnesium alloy, copper alloy, lead alloys, tin alloys. Okay, so these are the two important terms for that endurance limit or fatigue limit and fatigue strength or endurance strength. Okay, and the reason behind that, or what is the exact meaning of that term or that limit values that I have explained here. Then after this, we will move towards the fracture appearance. During this fatigue testing, this kind of fracture will occur. Okay, you can see clearly here this kind of fracture will be there. You can see whichever fracture or crack is there, it is through the grains. Okay, it is through the grains, and this type of fracture will be termed as transcrystalline or transgranular. Okay, this is the transcrystalline fracture or transgranular fracture. If two types of cracks may will be there, this is through the grains, and whenever a crack is through this grain boundaries, that will be intercrystalline or intergranular. This is the transcrystalline or transgranular fracture or crack. Okay. Now, if you observe under the microscope a particular cross section, then the fatigue fracture will be having this kind of different regions. Now, this region, this keyhole type region, this is the origin of the crack. Okay, keyhole type of region, this is the origin of the crack. Will be the origin. After the origin of the crack, in this way, this crack will get means it progresses and it will show you some smooth regions. Okay, up to this is the smooth region and this is the rough region. Okay, in this smooth region, growth of the crack is very slowly, that crack will transmit or it will progress, and in the rough region it will progress at a rapid rate. Okay, this is the rough region, this is the smooth region, and whichever lines are there, okay, these curved lines are there, these curved lines are termed as beach marks, or it is also known as the ripples, or it is also known as the striations. Okay, beach marks, ripples, or striations will be there, and these will be in the smooth region. Okay, this is the smooth region, and this distance depends on the vibration. Okay, this distance depends on, you can say that the spacing depends on the vibration, or you can say that whichever amount of stress is there, depending on that, this distance or spacing between these beach marks will change. Okay, so this is the appearance of the fracture, or you can say this is the nature. This is the transcrystalline or transgranular, means which crack will progress through the grains, and how it will this propagates, or different regions will be there. Origin of the crack in the form of a keyhole, then it progresses through a smooth region through the beach marks or ripples, and after that this is the rough region will be formed, and the crack will progress at a very rapid rate, and the component will get failed. Okay, then after the fracture appearance, the next point is to what are the methods used to avoid the fatigue failure of the component. Now these 6 points you can use to avoid the fatigue failure of the components, means you can do the surface hardening of that component. Here, for doing the surface hardening of that component, you can use different methods, like you can use carburizing followed by the hardening, and you can use the nitriding, or you can use different surface hardening processes. By performing the surface hardening processes, you can increase its fatigue life by performing different surface hardening processes. Then by changing the grain size of the component also you can change its fatigue life. Okay, if you change the grain size, means if fine grain size is there, then fatigue life will be more, and if a rough grain size or more or coarse grain size is there, then fatigue life will be very less, or fatigue life decreases. Then third point is the surface finish. Whenever fine surface finish is there, then it will automatically improve the fatigue life of that component. If a rough surface finish is there, it decreases the fatigue life of the component. Then you have to do the, or you have, while doing the designing, you have to use the proper or you have to follow proper guidelines, means you have to avoid the sharp edges or sharp corners. If any sharp edges or sharp corners are there, then at that some stresses will be there. It increases the stresses, means in short you can say that corners you have to avoid, sharp corners or some recesses may be there that you have to avoid. Then you have to avoid the decarburization in the sense loss of the carbon. If from surface carbon, loss of carbon is more, automatically its fatigue life will get decreased. Then corrosion, you have to avoid the contact to any corrosive medium. You have to avoid the contact of the surface to the corrosive medium. If it comes in contact with the corrosive medium, or in short, whenever corrosion is more, then automatically you can say that its fatigue life decreases. Okay, so these protection methods you can use to improve the fatigue life of that component. Then at the end, I have listed some factors that factors will affect the fatigue life of the component. Okay, generally 6 factors are there. If this rate, you can say that the rate of cyclic loading, and generally whenever rate of cyclic when a rate of this cyclic loading increases, then you can say that automatically the fatigue strength of that component increases. Okay, fatigue strength of the component increases. Then the next is the form of the stress cycle. Here form of the stress cycle is not having any or specific, or you can say that it is not having that much impact, or you can say that no effect will be there. Whichever form of stress cycle is there, it is not having any kind of the impact, but environmental conditions will provide some impact on the fatigue life. If suppose The you can say that in the vacuum or in the neutral environmental conditions, fatigue life of the component increases. Okay, as compared to the suppose one moist air condition is there and one vacuum condition is there, then in the vacuum condition the fatigue life will be more. And then size of the component means if size of the component is there, if a particular component is there which is having similar kind of the microstructures and other kind of the properties, then small sized component and large sized component does not provide any effect on the fatigue life. It will be having same fatigue life. Okay, then the stress gradient. Now whenever stress gradient is more, then it will decrease the fatigue life. Now here, what is the stress gradient? Stress gradient means you can say that rate at which that particular stress will change. At particular point, stress will be less, and again at the particular point of that component, stress will be more. This is termed as the more stress gradient, variation in the stress in the same component at different instant, different stress is acting. Then it is termed as the more stress gradient, and it will decrease the stress life. And last and most important, you can say that this is the temperature. Whenever higher temperature you are using than the room temperatures, higher the temperature, it decreases the fatigue life. And whenever you are using the lower temperature values than the suppose you have increased the temperature above room temperature, then its fatigue life decreases. And suppose you have decreased the temperature than the room temperature, then fatigue life increases. Okay, vice versa you can say that. So this is, or you can say that inversely proportional. Whenever temperature increases, fatigue life decreases, and whenever temperature decreases, fatigue life will increase. So these are the factors affecting the fatigue life of the component. In this way, we have discussed this fatigue testing along with how the fatigue test is conducted, what are the why the fatigue failure of the component occurs, then different types of the stress cycles, then the fatigue testing machine, and then what will be the fatigue curve obtained for different ferrous metals and non-ferrous metals, then fracture appearance, and the protection methods to, or in short you can say that the methods which you can apply to increase the fatigue life, and at the end factors affecting the fatigue life of the component. Okay, so try to remember this from this. This is the very important point. You have to concentrate on this for each. For creep test also, I have given you fracture appearance diagram. In some question papers of the universities, they have asked this fracture appearance. Draw the fracture appearance for fatigue test and for creep test. Okay, that's why I have provided you these diagrams. Please try to understand this, try to remember this. Okay, so in this way we have completed this fatigue testing. Now only one test is remain, that is the hardness test. And in that hardness test, different hardness testing methods are there that we will start in the next session. Now I will stop this session here. Thank you for attending this. Okay, please don't leave. I have some instructions to repeat. I will stop this session recording here. After that I will provide you some instructions. Okay, thank you.